And finally, let's look at pipelining performance and the limitations thereof. So this is going to use some of the theoretical math that we've looked at in other units, Amdahl's law and things like that. We start with the idea that a pipeline can be some number of stages long, right? The ones we were looking at last video was a four-stage pipeline, but we can have a pipeline of any number of stages, right? If we imagine a theoretical pipeline of Q stages, and instructions take, before we pipeline, instructions take T amount of time. So we're going to split up that T amount of time into Q chunks, and then each stage ideally takes T over Q time, right? Because we assume that we're splitting up evenly. Often we don't, but let's just start theoretically. There is going to be overhead added, because if we start with, say, a single cycle pipeline where the ALU feeds directly into the load store unit, if we're adding a latch between them, some time is going to be added. So we notate that as tau, and so the time for each pipeline stage to complete is T over Q plus tau. We're going to assume that all stages have the same overhead, even though we know that they don't, right? Because fetch, we're not even changing fetch. Program counter, instruction memory, instruction register. That was the same before we pipelined as after pipelining. So why do we assume the overhead is the same for every clock cycle? Because the whole point, why do we assume that the overhead is the same for every pipeline stage? Because the whole point is that we're lining things up so that they happen at the same time. So regardless of whether there is a pipeline stage that has no additional overhead or a lot of additional overhead, tau is going to be the maximal overhead that we have to add, because the clock cycle has to be consistent, because each stage has to be able to occur in parallel. So the stage time then is T over Q plus tau, and the throughput increase is going to be calculated by this formula. We're looking at the Q is the total number of pipeline stages, right? And we're going to have to multiply Q by tau, because we're adding that little bit of overhead every pipeline stage, right? So the question here is, how much longer does an instruction take to execute on this pipeline? And we start with, before pipelining, it took Q clock cycles. And after pipelining, it takes Q tau over T. And we have to add 1 to that, because we're starting with, if we start with this one, right, T over Q plus tau, this is the amount of time it takes for one clock cycle to execute. This is how much time it used to take for that clock cycle to execute. So now we've got this formula. And again, it looks a little bit like Amdahl's law. So we can get an idea of how that's going to work. So what we find then is the limit of pipeline performance is going to be in this tau, in this extra time it takes to add, tau over T, right? So compared to the entire execution of the instruction, how much extra time is going to have to be added based on this pipelining, right? As we increase the number of pipeline stages, Q, the amount of time to execute each stage, T over Q, is reduced, right? If we have infinite stages, we can break up an instruction into infinite tiny, tiny pieces and overlap them all up. Then the clock cycle is reduced to almost nothing, but there's still going to be that overhead. And that is like the unparallelizable part of Amdahl's law, and that means that that overhead is going to be our limit, if we assume that everything is equal, and if we assume we can optimize for these throughput cycles. In reality, we don't want infinite pipelines, because the longer the pipelines are, the bigger the impact when they stall. And they will stall, regardless of how good your branch prediction is, regardless of how good your in-order, out-of-order execution is, you're going to get pipeline stalls, and those are going to add a lot more waste than a tiny little tau in a tiny little slice that you're adding. So we can optimize our throughput in this way, but the reality is we're going to get much better performance optimization in the practical world when we try to improve our branch prediction, try to reduce the number of stalls, and we make these trade-offs by saying we don't want a really long pipeline. We want a pipeline that's enough stages to really optimize our performance, but not enough stages that the stalls are going to be really problematic, right? This is the idea of pipeline stages. Theoretically, more stages is always better. But in the real world, with real execution, Too many stages means we pay too much for pipeline stalls, right? We get more difficult branch hazard problems. We get more complicated data forwarding. All of this kind of stuff means that longer pipelines are not necessarily going to be better pipelines, right? Pipelining is complicated when we're doing jumps and branches. Pipeline is complicated when we're doing any of these kind of changes in direction, when we have to say we're going to do this thing instead of that thing. We talked about pipelining for branches. Jumps is even worse because a jump is unconditional. When you get to that point in the pipeline, you know you're going somewhere else. But you don't know that you're executing a jump until you decode the instruction. And by that time, you've already fetched the next instruction. So the jump always incurs a single bubble because you've already started this instruction, even though that is not the next instruction. If this is a jump, the next instruction is over here somewhere. So jumps always incur a bubble, or, right, in the same idea as branch or loop unrolling, right? If the assembler is clever enough, it can go and look up what the next instruction is in the subroutine or whatever and insert that instruction instead of the next instruction after the jump so that you can carry on without a pipeline bubble. Everything is complicated with pipelines, right? So branch prediction is the next idea that we're going to look at, and we'll look at that in the next video.